Hello, I would like to introduce the fourth tutorial in the Rooibos series. Just to make sure that it works, we have it here. And you want to go to tutorial 4. I've already downloaded, so I will do that. But of course, you can right-click and download on this. It should be there. And let's take a look at what it looks like. Here we go. All right, so let's start at the top. I'm going to clear all of the output because the output is not current. So let's see what we have here. So it says this tutorial will use different machine learning methods, logistic regression and random forest. Actually, I have changed it. So right now it just does logistic regression. Next week we'll do random forest. We'll be modifying this one. So use a pipeline to organize your training and testing. We did this already with Mahalanobis, and we're basically going to reuse a lot of the code and procedures that we use for Mahalanobis. Apply hyperparameters. We've talked about hyperparameters before. Here we're actually going to put them into the code. Now, Mahalanobis needed no hyperparameters, but this one, logistic regression, does use hyperparameters, and we'll talk about that. And then compare these methods against each other and a baseline using jackknife. So we introduced jackknife in Mahalanobis. It's a way of estimating the uncertainty in your accuracy estimate. All right. So let's start here. This should be familiar, downloading the packages, the data. This comes from the tutorial, the third tutorial. So you should have this from the third tutorial. This is the Mahalanobis results. If you don't have your Mahalanobis results, then let me know. We'll work that out. Please let me know. Okay, so let me just start this and run it. Okay. All right, so logistic regression is a leading machine learning method. Let me make this a little bigger so you can see it better. Okay. Later on, we'll use random forest, which is another common method. We compare the results from multiple classifiers. Okay, so we're actually going to look at different versions of logistic regression. First, we create aliases for the classifier and create a list to use when we apply the classifiers one by one. This is kind of like what we did with Mahalanobis. We used different feature sets, and we used a dictionary to keep track of them. So we'll be doing something different here. For our initial trial, we'll be using two variants of logistic regression, one with or without fitting an intercept. Now, basically, fitting an intercept means that the line or plane that separates between the two classes can be any line, while not fitting an intercept means the line of separation must pass through the origin. So let me quickly show you what I'm talking about. So I don't know why I have this black garbage there. It seems to be permanent, but you have to pardon me. All right, so here, let's go ahead and start this. Let me get out my tablet and look at this. If we have two features, then we would plot those two features on a plane. Looks like my tablet's not quite working. Let me pause while I get this working. Okay, I think I'm back in business here. So let's take a look at a case where we have two features, feature 1 and feature 2. Then we have two different classes. So I'll make the red class and the orange class. So these are data points, something like this. And then we'll also do the data points for my green class. So these are data points. So these, for instance, would be samples where the green, say, would be fermented and the red would be non-fermented, something like that. Now, if you have without intercept, basically, logistic regression draws a line between these two. It separates them with a line. Now, if I better put a different color for this line or it's going to make it red. All right, and I guess I have to go back here and do this again. Let's see if that works. All right, so now, if I do it without an intercept, that means that the line of separation would have to go through the, whoops, I don't know why I did that. The line of separation would have to go through the origin. Now, if you have with intercept, you can do a line of separation that's not through the origin. And you can see if you don't have an intercept, you do have more freedom. So probably we expect to get better results if we don't use the intercept. All right, so let's see how that works for us. All right, so we're going to do those two variants. All right, so here we have logistic regression, and we're going to define two models. We're going to use logistic regression in both cases. Later on, we'll replace one or both of these with other machine learning methods. And this is the model. This is a routine from scikit-learn. If you look up here, we've imported this from scikit-learn. All right. And scikit-learn is the Python library for machine learning. All right. So we have this list of models that we're going to use, and then these are the names that we're assigning to these two different models. All right, so let's go on here. Now we have machine learning has hyperparameters. I've talked a little about hyperparameters. Now, the hyperparameters in logistic regression are shown here. You can go through this and look at this. They have all of the hyperparameters, quite a few of them. Some will make a difference in our case, some will not. A lot of these don't make a difference when the number of parameters, number of features is small, and they're more important when there's a large number of features. For instance, the L1 and L2 regularization. We're going to be looking at both of these. But L1 and L2, so here's, I do give a description that the L2 penalty with logistic regression tends to equalize more the size of the regression coefficients, while L1 tends to favor more the coefficients for those features that are better predictors. All right, so, and then this is a nice article that you can read about regularization. So we're going to use both of these regularizations, and we're going to use grid search to find the best alternative for other parameters as well. So later on, we'll use random forest. Here's a reference for random forest. You can pass over this for now. So these are two different solvers. You can consult the documentation for that. Then you have these values. This is what we're going to do using grid search. We'll be trying all of these. This is L2 and L1, my two penalties that I mentioned above. All right. So this is the parameter set for logistic regression with fit intercept. Without fit intercept, you're the one to do this. Okay, it's going to be a parallel statement, so you have to complete the code here. And your parameter set for non-fit intercept, you'll call that NFI par. So it's going to be a very similar statement to here. Only you have to set another option as false. All right. Now, to set up the training and testing sets, we need to specify the feature sets and the outputs and the training testing split. We'll apply each machine learning method to 4 different feature sets. I think it's actually 3. I'm going to change that because I'm just going to do 3. Okay. And we'll compare the performance. Looks like we're doing them all with H2O and see how that works out. Okay, the code is very similar to the code we did for baseline estimator. If you look back at the Mahalanobis tutorial, you will see a very similar code to this. This time we'll take the 2 best feature sets from the baseline and the best split. Right. Okay. Actually, this is not true. So I'm going to erase this statement. This is not what we're doing. Okay. We're here in this case, we're doing the different pairs of water features. And of course, we could do the same for methanol. We probably get better results. Okay. Let's see. This should be defined split. Okay. So now. All right, now here's where you're going to be basically copying the previous code. You have to train and evaluate multiple classifiers. This is actually just 3 different feature sets. So let's change that to 3. Okay. With 2 machine learning models. And of course, these models also, we're trying different options for these different models. Okay. All right, so for this purpose, we define a function, getAccuracyML. You may remember the getAccuracyMaha, which computed the accuracy for the Mahalanobis estimator. And these have the same outputs, the total accuracy, the standard deviation for training, testing, and total. Now, we're actually not going to use training and testing separately. Training and testing are used together to get the total standard deviation. Okay. This getAccuracy the procedure is different from Mahalanobis. You're going to use something called cross-validation. Okay, so you can find out about this in this Jason Brownlee's blog, which is a very good source for information about machine learning. All right, so here we got this. Here you can see that we have stratified k-fold. That's a cross-validation method. Here we have this routine called CV that actually performs the cross-validation for us. So you don't need to know all of the details here. If you're interested, you can certainly look into scikit-learn and see how this is working. Here, M is the method, P are the parameters. Here we have the training set and the testing set. We're going to use accuracy. We're going to use accuracy to train. Now, this is done on the. This will be done on the training set. And see, you're going to fit this on the training set, and then you're going to test it on the testing set. So YPred will be the predictions of fermented, non-fermented, based on the testing set using the using the estimator that is trained from the training set. So these are the predictions, and you need to compare this with your actual test results. When comparing the test results, the actual classifications of the test samples, these are the actual classifications. These are predicted from the classifier. You're going to compare these two and use those to find the accuracy. Now, you should know how to figure out accuracy from an array of true classifications, which is going to have zeros and ones, and an array of predictions. Basically, you want to count how many agree and divide by the total number. Right? So that's code that you will have to add there. And that's what you'll put into result. Result is going to be a floating point number. It's a single number. All right. So this get accuracy ML is similar to get accuracy Maha. And again, you can refer back to that previous code. This one is going to call this cross-validation to get the classifier, the trained classifier, that is then used to compute the accuracy. So you can see that here. We set things up here. Here we find the total accuracy by calling CV, and we're going to do similar to find the accuracy when you leave out one training sample and when you leave out one testing sample. All right, so the testing sample is going to be similar to the training. Okay, you're going to compute from these arrays, just like with Mahalanobis. You're going to compute standard deviations for the training and testing and for the total. Here I gave you the equation for total. It's the square root of the sum of the squares of the standard deviations. The square of standard deviation is variance, so it's the square root of the sum of the variances. If you have two independent estimates and you're adding them together, then if you have two independent factors and you want the variance of the total, you want to add the variances. Variances add, standard deviations do not add. Right? So you'll see that when you take probability, and maybe you've heard that before in a probability course. Right. So from this, we get the total accuracy and the standard deviations that we need. Now, here again, we're taking a cue from Mahalanobis. We've got a dictionary to store our results. We have dictionary base. We have our Mahalanobis results. That's for the baseline. And then we're going to create another dictionary for the machine learning results. So that's MLDix. Okay. So here we have the different models. So this is where we're going to call our function here, our get accuracy ML function there. That's where we're going to call it. And we do this. We have create keys. The keys are organized a little bit differently from before. You can see here that this key is created as a string from the splits and the feature set. So that's combined into a single key. When we did the baseline, we had those as separate keys. It's just organized a little bit differently. Okay, so here we're putting the accuracy into our dictionary. Key 0 will be the method. Key 1 will be the particular feature set. And then you put this in total accuracy. Now, if you go back to the Mahalanobis, you'll see that what you did was you put the training, testing, and total standard deviations under subkeys on the same level as this. So you're going to have a subkey on the same level as total accuracy, both for training, testing, and total standard deviation. You're going to need all of that. All right. So you've got 3 levels. Don't make more than 3 levels. It's just 3 levels. You're not going to put something under this one. This is just for the accuracy, right? So we have this. So here's some exercises to make sure you understand that. We're going to put the results in an array, just like we did with Mahalanobis. Go back to Mahalanobis and see how this was done. We put the accuracies in an array. We put the standard deviations in an array. Okay? And this is the total standard deviation, not the standard deviation. See, it's the total standard deviation. not the training or testing standard deviations. All right, here you can print just to make sure it's correct. Here you're going to have the error bars, print out the error bars. That's just like before. Now here you can also go back and see how to do this, how to label ticks, how to put a legend, and so on. At the end, whenever you show a plot, you should have this statement plt.show. It just makes it nicer, and otherwise it shows some extra verbiage that's not necessary. All right, so I want you, when you get a graph, I always want you to think about what it means. Right. So which estimator appears to be most accurate and which is most stable in terms of small error bars, but is the difference statistically significant? Okay, you can mention both which appears to be best and whether the difference is statistical significance. So does including the intercept fitting provide any advantage? So we're going to do intercept fitting, non-intercept fitting. You can see if those look any different, significantly different. All right, now we want to compare these two results to our baseline. And the baseline was Mahalanobis. So I'm just going to refer to that. This is Mahalanobis. Mahalanobis. Okay. All right, so we'll compare. All right, this is something very important. It's often neglected in research, or people want to publish new things, but you should always compare something new to something old, because sometimes the old is better. All right, so our Mahalanobis baseline, our best classifier was TPC and TAC. And so we're going to compare that. So this is from the baseline dictionary. This is the Mahalanobis result. This is the accuracy. Right. Now, you also are going to need to have the baseline variance. Variance is the square of the baseline standard deviation. You should be able to get the standard deviation also from the dictionary using a similar statement. Okay. We're going to compare all these other models to these baseline accuracy and standard deviation. All right. So first you need to create lists of the relative accuracy and the standard deviation of the difference. Now, the relative accuracy will be the accuracy of the new method, which is here in this new ML-Dix dictionary. Okay, and you're going to subtract the accuracy of the baseline. Accuracy of the baseline is given here. Okay, so that's going to be the relative accuracy. If this is positive, that means that the new method, the machine learning method, is better than the baseline. If it's negative, that means the baseline is better than the machine learning method. All right. Now, when you have a difference, the difference also has an uncertainty. There's a variance or standard deviation associated with this difference. Now, the way you get standard deviation of a difference is similar to the way we got a standard deviation due to training and testing variation. You take the sum of the squares of the standard deviations due to each one. All right, that's what it says down here. So you want the standard deviation of the difference, which is the square root of the, let me pull this down so it looks more clear. Sorry. Get this, okay. All right, so make sure you get this. So you're going to append that to this array. So you're making an array of accuracies and an array of standard deviations. Very similar to what we did with Mahalanobis, okay? All right, so it's arranged the very same way. So trying to emphasize that you reuse a lot of procedures. So once you really understand the basic procedures, then you can reuse your expertise in many situations. And that's why I've spent so much time on these fundamentals, because I guarantee if you get into this area, you'll be using these kind of techniques. Okay, just print out the results. And here you're going to do the plot. Again, you'll have to do some labeling here. And then I want you to think about your plot, summarize your results. Are there any estimators that appear to improve over the baseline? Is the improvement statistically significant? The baseline will appear as a black line, and the others will appear as points with error bars. So if you're confused about whether your output is correct, you can always send it to me. Let's have some interaction here. Don't wait till the end to work on this. Have it due on Wednesday, but please don't wait till the end, because there's probably going to be several iterations. What I'd like to do is, as soon as you're finished this, we can have a meeting and we can talk through and see what makes sense, what doesn't make sense. I think that's a lot better way to give you feedback than to just write something, because there's a lot of little things that can be wrong or be right. And actually, when I talk with people, it helps me focus. All right, so let's go ahead and stop, and hopefully this will be useful summary.